So, Frederick started out by complaining. I'm going to start by thanking the organisers, which is perhaps more traditional and slightly more boring than it actually meant. Now, I'm going to be talking about a project which I've been working on with Deraux and Paupert for, it seems like forever, probably I think it started around about 12 years ago. And I've given variations on this talk all the time. Most of the time, I'm giving it to a non-specialised audience. And so it has a whole lot of stuff at the beginning, and some history and some stuff. Because this is a specialised audience, I decided that I'm going to try to describe the geometrical construction that is at the heart of what we're doing. And I'm going to be very light on definitions and history. And if you want some more definitions of history, I'm around for the next few weeks, and we can even have an informal session. Okay? So I think everybody in this room knows what a lattice is. And if you don't, it's a discrete subgroup of a Lie group with finite covolume. And I'm now going to talk about, so that's that word. So arithmetic groups, well, I will give you a one-sentence definition of an arithmetic group, and then I will show you what the criterion you use to determine arithmeticity. So here I'm going to have my favourite Lie group, which in what follows is going to be PU21. You can use your other favourite Lie group, and we had a whole list of them yesterday. And I'm going to then think of curly G, which is going to be an algebraic group. Defined over Q. I'm going to have GR, the real points, and GZ, the integer points. Then this is an arithmetic subgroup of the real points. This is the definition, actually, of an arithmetic group. But that's usually not a very useful place, because I'm not usually interested in my linear algebraic group, which can be sort of big and scary. I'm interested in my favourite Lie group. So I'm going to then have phi from GR down to G, which is going to be continuous surjective morphism. And the key thing is it should have compact kernel. Then, if gamma is a subgroup of G, and that is commensurable to phi script Z, then gamma is an arithmetic subgroup of G. So that's sort of the usual general nonsense, and if this was a non-specialist audience, I would kind of work through in slow detail the first baby example, which I guess probably most people have seen, and if you haven't seen, I'm happy to do that informally. So the only little bit of history that I want to say, we've been caught on film being clumsy, never mind, is that, so all arithmetic groups are lattices. Durham and Chapter. And all lattices are arithmetic, except when G is commensurable to SON1 or SU. So for higher rank, that's modulus, and for the other rank 1 groups, which are SP, N1, and F4 minus 20, that's due to Corlett and Broad-Moffett. Okay. So actually, I'm quite happy to restrict myself down to, well, to these two groups. It's known that there are infinitely many non-arithmetic commensurability classes here for all n. So that, and this is the most interesting case. So n equals 1, that's commensurable to SO21, and we have infinitely many there. You can see that for two reasons. A cheap reason is we have Teichmuller theory, so there are uncountably many lattices, but there can only be countably many arithmetic rings. A slightly less cheap way to do that is Takeuchi told us exactly which triangle groups are arithmetic, there's only finitely many, and then you can easily construct infinitely many commensurable classes there. So that was n, so n equals 1, but here n equals 1, so we have infinitely many. N equals 2, which is the case I'm going to be thinking about today. They were first constructed by Mostow in 1980, and in some sense our project is very much in the spirit of Mostow. N equals 3, there's exactly one example known, that's due to Deligne and Mostow. N greater than or equal to 4. Everybody says. If I get n, it exists for n. So this would be, sorry, this is non-arithmetic. These are the non-arithmetic. So the next piece of history was that Deligne and Mostow in '86, reinterpreted by Thurston a few years later, produced a list of non-arithmetic lattices in SU21 or PU21. It's best to work in PU21. And no more examples were found until the project that I want to describe for you. So there was basically nothing happened for 25 years or so. No, people looked for examples, they couldn't find them. All the examples that were constructed ended up being back on the So then we produce these new examples. So that's my background, which would normally have taken half of the talk or so.
Yeah, just a little question. So the one Livni example is also.
So what's that? The
Livni
example is in the Deligne Mostow list.
Ah, okay.
So Mostow in 1980, Livni in 81, and then Deligne and Mostow.
You say they are compact or co-compact?
Compact or non-compact. I mean, finite. They've all got finite volume, but either arrives. And in our examples, it's roughly half and half.
What about the n equals 3 example? Is that what co-compact or non-compact?
That's non-compact. Okay, so I'm going to focus on PU21, which is the homomorphic isometry group of complex hyperbolic 2 space. And complex hyperbolic 2 space, for the purposes of this talk, we can think of this as the unit ball in C2 with the Bernoulli metric. So this is just a generalization to higher complex dimensions of the Poincaré disk with a Poincaré metric. So just as you can think of the sphere as being Sn and generalize, so S2 and generalize to Sn in the real direction. You can also think of it as CP1, and you can generalize to CPn in the complex direction. And once you leave this small dimension, these two things are different. So in this same way, this is the non-compact analog of that. This is different from H4. That has non-constant curvature. So the key thing that has been was in Mostow and essentially in all the other examples, these are groups generated by complex reflection. So I want to tell you about complex reflection. So if I have this is supposed to be my unit ball in C2. Now, Frederick says that backballs are too small. I just say they're too low dimensional. I can't possibly draw four-dimensional pictures accurately, but you'll just have to use your imagination. So, and then I'm going to think about a complex line in here. So that's just the intersection of an affine line in C2 with that ball. And I think of this as the mirror of my complex, my reflection. This will be a mirror. Now what happens in the, so let's just draw a picture in, drawing that as a line, because that just helps us to think about this. If it was a real reflection, what would happen? I would have a normal direction, and then I would decompose my vector, something here plus something orthogonal, and then my reflection would be, I would just go in the opposite direction. This is what we do in linear algebra. As we're working in the complex world, then my orthogonal line is now a complex line, and here I now have an angle. I have a complex reflection to an angle theta. So in other words, I can rotate around here so it equals theta. Now, it's not a very satisfactory term because most of us like to think of reflections as being involutions, but this term complex reflection dates back at least to Shepard and Todd in the 50s, and so we're stuck with that. In all the cases I'm going to be thinking about, groups generated by R1, R2, R3, which are going to be complex reflections. Angle 2 pi over p, and p is an integer, and p is greater than or equal to 2.
Same p for the three?
Same p for all three. Okay, so if I have this set up, how many parameters should I expect in my parameter space? If I was doing real triangles, you would expect there to be 3 parameters, which you can think of as the 3 angles, the triangle, or the 3 side lengths. Here there are 4 parameters. And what I'm going to give you during the talk several equivalent ways to parameterize this.
What's the matrix reflection?
Oh. Okay, so one of the things I haven't told you is that I have a Hermitian form floating around, just like I had, like I would have if I was thinking of the projective model of the real hyperbolic. And now I have a Hermitian form or a quadratic form, and so I could think of, if I have n is a normal vector to my mirror. So this normal with respect to the Hermitian form. So i.e. Then my reflection would be, well, how do I normally do this? I take something in the normal direction, so that would be so that just gives me the identity. So in the mirror, everything gets fixed, and in the normal direction, I multiply by e to the 2 pi I. So that's going to give me a rotation. If you like, you could think of your matrix as being e to the 2 pi I. As p. Again. Okay. A standing piece of notation, which I probably will forget to tell you, is that it's just useful to me to write u as e to the 2 pi I over 3p. It's just, otherwise it gets a little bit writing the same thing over and over again. So I've got, I'm going to give you one way of parameterizing this. I told you I had 4 parameters. I'm going to give you, actually I'm going to give you 3 complex parameters, so I'm actually over-determining, and I'll tell you what the ambiguity is. So I'm going to have rho, sigma, and tau, going to be my parameters, and these are u squared minus u bar times so n1, n2, n3 are normal mirrors of R1, R2, R3 respectively. And you can guess what the rest of the others are. Yeah. Over norms. Okay, so given that information, I can immediately construct my Hermitian form, just like I would do if I had a Coxeter group. I could construct a Gram matrix, just using the sort of the data associated with this. Now I'll tell you what the geometrical significance of these parameters. In fact, this is overdetermined because I can multiply these by scalars, and so in fact it's only one of my parameters here, one rho, one sigma, one tau, and the argument of rho sigma tau. Those are parameters, and everything else I could switch around if I multiply through my scale, these things by scalars. So I have a choice of these normal vectors.
So these are basically just like the angles between them.
So these are somehow like the angles of the triangle, and then this is something like the Cartan invariant or the Toledo invariant of the triangle. All right. So let's think about I want to come back to how we can geometrically interpret this. But this is all going to be part of the general theme. And I want to interpret these parameters geometrically and in terms of traces of elements of the group. Now, if I was in the real world or in the plane, and I had reflections in a pair of lines like this, then there would be something significant about this angle, namely the product of these reflections would be a rotation through twice that angle, as we all know. And if we want to play the game of Coxeter groups, then you would want that angle to be pi over an integer. Right? So a similar sort of thing is going to happen now. So I have my two complex lines. Remember that in 4 space, 2 complex lines intersect at a single point. And then I want to think about what happens with the product of those reflections. Now, if these are complex reflections of order 2, then I want to think of them as being an angle between them that's like this pi over n. But when I have higher order reflections, this product, there's something slightly more subtle going on. And in fact, what it turns out is that they should satisfy a braid relation, and the length of the braid relation is related to that angle. So I want to think about braid relations, generalized braid relations. And so I'm going to write, if A and B are capital A and capital B complex reflections, or in fact, any symbols, I want to say they satisfy braid relation N, which I will write as BR B is N. Well, I perhaps actually want to try to say BR sub N, using this to be the minimum length of the braid relation that they satisfy. If we have that AB to the N over 2 is BA to the N over 2, and when N is odd, this should be interpreted as you start with the same letter that you finish. So, for example, when N equals 3, I'm going to get ABA is BAC. So it's a sequence of length. And if these are involutions, that means that AB would have order n. So this restricts to what we're familiar with from this picture. In the case where we have involutions, so this is really the correct statement that actually we shouldn't be thinking about the product of these things having order n. We should think of them as satisfying a braid relation. That's always a bit too much of a mouthful. Right, so
Condition for discreteness of the group generated by 2 elements?
that's yes. Okay. So this is where I can now start to think about some braiding lengths as being my parameters. Leave that up to remind you, because we don't need it again. Okay, so if I've got A and B, I'm going to think of these in SU21 for a moment, and they're going to be complex reflections. So for example, that means that their trace of A is trace of B is u squared plus 2u bar, because I'm wanting the, which is really u cubed plus 2, which is what I had before. But to turn this into a matrix with unit determinant, I have to multiply by u bar. That's why I have it over 3p over there. And then if trace of AB is of the form minus 2u cos 2 pi over q plus u bar squared. Okay, so stop a moment. The mirrors are each u bar eigenspaces for A and B, so their intersection point gives me a u bar squared eigenspace for the trace of AB. So then you can see that I can read off the rest of the eigenvalues. So Q is another Q, right? So Q, well, okay, we could just say, well, I'm going to say 2 pi over Q because I'm going to abbreviate things. Right? And that's going to be the same as the braiding length of A and B is Q. And so that's the equivalent of this angle pi over Q between the. Now, if I come back to my original parameters, the trace of R1, R2 is 2 minus mod rho squared u bar, u plus u bar squared. And so that would mean then mod rho would be cos pi over q, 2 cos pi over q. And so I can relate my parameters rho sigma tau to something to do with braiding. And similarly, again I've got this written down here, trace of R2, R3 is 2 minus mod sigma squared u bar squared, trace of R2, R1 is 2 minus mod 4 squared u plus u bar squared, and trace of R1 3 bar R3 inverse R2 3 is 2 minus sigma tau minus rho bar squared. So this number, I want to assume that these two satisfy a braid relation, and so I can relate the absolute value of this to a braiding length like I had there, right here. Similarly with this one and this one. And this is going to be the corresponding to the mirrors of R1 and R2 inverse R3 inverse R2 R3, which is another of the complex reflections in the group.
Again, do you take the same Q for the 3 or
No.
No.
And and you can see from this, if I expand this out, I can solve to get the real part of rho sigma tau. And so for each of these sets of braiding lengths, I'm going to get two possible solutions depending on the choice of the imaginary side part. So I've got, so these four numbers will immediately determine the four numbers which I probably erased now of mod rho, mod sigma, mod tau, and the argument of rho sigma tau up to plus or minus.
John, you keep talking about grading, but just to be sure, I mean, you could just say, well, you're really just fixing these angles, right? I mean,
Yeah, I'm effectively fixing some angles. Yeah,
but it's maybe harder to figure out.
but as this is geometric group theory,
Right.
and we're going to get some we're going to get some presentations,
Sure.
and it's sort of quicker for me to go straight into braiding rather than angles. But it's angles, it's braiding, it's traces. So what I end up having is I have 4 numbers which we call A, B, C, N is the usual way. I think Rich calls them P, Q, R, N in his papers, but I already, following Mostow, we have this angle of 2 pi over P, so I don't want to confuse that. And so these would be the braidings, the 4 braiding lengths. So if I fix P, which is the angle of the reflection, and these 4 numbers, then I completely determine my group, except that I might possibly have to complex conjugate. So actually determining 2 different groups.
So you give the image of a triangle. So ABC would be braiding
For
lengths
R1, R2, R2, R3, R3, R1,
and
and R1 and the second
this
relation.
last combination.
And of course, this doesn't uniquely determine the group because I could choose a different set of generators and I'd get a different quadruple. Right, so there's a general principle which we believe, it's a working hypothesis. It's far from proved, but this is the working hypothesis that we're going to assume that R1, R2, R3 is lattice. I won't quite say if and only if, that's supposed to be a, it should be if and only if R1, R2, R2, R3, R3, R1, R1, R2, R2, R2 inverse, R1, R3 inverse, R2, R3, R1, R2, R1 inverse, R3, R1, R2, R3. I've all got finite order there. Well, I've all, or I should say, non-box together. There are certain cases where they can. And because I hate writing R's too many times, this is going to, I'm going to just use number notation. So this is going to be 1, 2, 2, 3, 3, 1. This is going to be 1, 2, 3. And again, I don't like writing inverse, so I'm just going to write bar. And that's, you can think of that as not complex conjugation. This is, again, it's not 12 and 23. Okay. And this is 1, 2 bar, 2, 3. 1, 2, 1 bar, 3. 1, 2, 3. Sorry, what?
Sorry, can you say again what's ABC and N? Sorry. ABC.
So these would be the braiding lengths of this person, this person, this person, and this person. And obviously, I could cyclically commute the generators to say this person, this one, and that one, or with that one. So, okay, so there's lots of ambiguity here, but at least it's going to determine my group. Right. How are you doing? I think I started a little late, but I'm definitely very slower than I thought.
I'm sorry, I don't get what you mean by working hypothesis. I mean, is this true, or is like one implication true, or are you going to explain now? I don't know.
It's as far as we understand, as we believe, then all the examples we know have this true, right? Obviously, we need more than this in order to show that it's a lattice. Otherwise, I'd immediately have infinitely many examples, right? But it's a sort of a way of sort of some rough sieve that I can throw away lots of things. And I mean, Rich has a very beautiful paper, which is part of the inspiration for this construction I'd like to describe, which we always know as rho chi. So Pierre said I should write something vertically in the Chinese style, but I could write this as rho chi, which is real hyperbolic on the outside, complex hyperbolic on the inside. Right.
So it's a conjecture you don't want to make, is what you're saying?
Yeah,
It's a question.
yeah. It's. I mean, it may be that there are other things out there that look different, but when you look at Rich's paper, he did some constructions for where I think it was 1, 2, 3 was not finite order, and then you get a very similar picture to ours, except instead of we're going to see something closing up, whereas his just carried on forever. It could be there would be some really bizarre way for it to close up in a different way that we don't know about. But
I see, so this is not a necessary condition for
We
the group to
believe-
be a lattice.
we
and
believe
not-
that it's necessary, but we don't. It's
You
way-
and
you could say,
not sufficient either.
No, it's certainly not sufficient.
Okay.
so you could say that the words of length 3 and 4 at most 4 seem to determine whether or not the thing is discrete.
Yeah,
That's a way of saying it. But it's just an experimental
yeah.
thing with some support.
Do you know if the conjugacy class, the group generated by R1, R2, and R3 is determined by the traces of these words?
Yes. Yeah. So I could write the case of 1, 2, 3 is rho sigma tau minus 1 rho square minus 1 sigma. So as I can already determine, again I have this ambiguity of whether it's a rho sigma tau or rho bar sigma bar tau bar, which would just be the corresponding 1, 2, 3 or 1, 3, 2. Right. Okay. I want to be able to tell you the arithmeticity criterion we use, and I will just quickly state that. Nicely written down. There we go. So this is Mostow criterion. Follows Takeuchi for Fuchsian groups and Lindbergh Coxeter groups. So L is going to be a purely imaginary quadratic extension, totally not totally real in the field. Okay. H is going to be a Hermitian form. Find over L, signature 1. And then we suppose that gamma, which is a subgroup of SUH with entries in the ring of integers of L, is a lattice. We assume that we know that somehow. Then gamma is arithmetic if and only if for all Galois automorphisms L which don't induce the identity of Q of the traces of the adjoint representation of gamma.
So morphing over Q, not over K. Gamma morphing over Q, absolutely.
Over Q, yeah. Gamma over Q. Not inducing the identity on that, then we would have the corresponding form H sigma. H sigma should be definite. Positive definite or negative definite for negative decay. And the connection with what I was saying earlier is you go up to your algebraic group, which is going to be given by taking copies of everybody in each of the Galois conjugates, and then you would just project down to the factor that you're interested in, and the kernel should be compact, is exactly the same as if the unitary groups of these are compact, all the non-trivial ones are compact, and that would be exactly if the form is definite. That's you apply this Galois automorphism sigma to the Hermitian form H.
The coefficients.
Yeah. So, for example, if it was 1, 1 minus root 2, you would go 1, 1, 2. And that's the basic baby example that you. Okay, so if we have that, and there exists sigma where sigma H is indefinite, then the group is automatically non-arithmetic. And that's something that's very, very easy to check because we already have my form given by rho, sigma, and tau. So I'm really working over, well, I might be working over the Q where in all the cases I'm interested in, they're all roots of unity. So they're all algebraic integers. Most of the cosines are roots of unity. And they're all algebraic integers, so I'm in a number field, and then I can just really easily check this. So that's how we show arithmeticity. That's the easiest part of the whole.
So how do you tell that it's totally real? With all the roots of unity that are going to appear, how do you get a totally real one?
So if I have,
Why is it totally real? Why is the field, the number of field you get, why is it totally real?
because I want to have only basically one complex place, or one, yeah.
Yeah, no, never mind.
Yeah. So for example, if you think of that's a quadratic extension of Q. Right, so that would be my K, and that would be my L, for example.
Is it true every lattice will have a trace field which is a non-field, right?
Yeah.
But is it true that you can put yourself inside the trace?
Yeah, I mean, this is but from all the things I've told you, I can just write down where I can write down things.
But you have this suppose gamma belongs.
Is a lattice.
But if you just start with a lattice, then do you know whether?
Well, I'm starting with a triangle group, and then that's automatically given to me in this form. I mean, it could well be that if you're starting with a lattice, it might take you a little bit of work to get it into this form. And that's a different question. Right. Okay. So here is my combinatorial model I wanted to talk about, which is heavily based on my interpretation of Richard's rho chi paper, and then kind of, I think we somehow went a long way beyond where Rich went, because he was going in a slightly different direction. So let's start out with a pair of complex reflections. I'm going to think of them as being, I've got B, I've got C, complex lines, and maybe then I could think of as B, so this is B is the complex line, and then B is the complex reflection, and this is C. C would be the complex reflection here. And then if I look around, I can just pretend that I'm doing the usual thing with reflections, right? And so I could look at B, look at C, and so my reflection here is B, C, B bar. We do the same thing in the other direction, I get C bar, B, C. And then these lines somehow, I shouldn't have drawn them sticking out like that. They come around, and this closes up, provided at some point I have B, this is C bar, B bar, something, C bar, B bar, C, B, something is the same as the same things, but the opposite way around, which is because of the braid relation. So, for example, I can do B, C, B, C, B bar, C bar, B, C, B bar, C bar, B, C, B, which is B, C, B, C bar, B bar, because of the braid relation. Okay. And providing that because of my assumption that my braiding angle was 2 pi over an integer, then geometrically they're going to appear in the right order. At the moment I'm just doing a combinatorial model, so I can write them in whatever order I like, and I'll choose to write them in that order. So now let's think about another complex line, which basically makes up the base of this triangle, which I can call this complex line A, and its complex reflection will be A. Now, in CP2, all pairs of complex lines meet in a unique point, so I can sort of continue this around, and that looks like a bit of a horrible picture, so I'm going to draw it much more like very suggestively like a pyramid. So this whole of this base is going to be correspond to A. And then I'm going to do what I did before, B, C, C, B, bar. So I can start out doing this with 1, 2, 3, which would be my original set of generators. And of course, I keep on, 2, 3, 2 bar, and 3 bar, 2, 3. And I'm going to assume that as I do this, when I come down each pair of these that I'm going to hit at the base, they're going to braid in exactly the same way like this. This is an assumption. Right? We've already seen by assumption that these 4 people all braid to finite order. I'm now going to assume that the same is true here, and however many times that I need around the back. I'm going to be making a whole pile of assumptions which start to sound preposterous at some point, but actually they work in a surprisingly large number of cases. There's a number of groups that we're going to get, which includes all of the Deligne and Mostow groups. It's going to be at around about 80 groups that we have. Okay. There's not going to be so many that are non-arithmetic, but this works for lots of arithmetic ones as well. 80 doesn't sound like a big number, but it's big enough for me. Okay. So I have one of these pyramids, and this is going to be my building block for building a fundamental domain. So I need to do 2 things. First of all, I need to work out where, I'm going to be using a Poincare theorem, so I need to look at where does this get mapped to under a side pairing map. My side pairing map ought to be one of these complex reflections, so I ought to have another one underneath. Now I've got some choice involved. Yeah?
So you're fixing a group, and this is going to be a criterion for showing that the thing is really
Yes.
the lattice.
Yes, exactly. Okay. So at the moment I'm just telling the general procedure, but at some point, we're going to apply this in very concrete cases with, seriously speaking, with 40 numbers. Okay, so I want to be able to choose in a sort of automatic way what the side that comes underneath is. It's going to be some power of this complex reflection, but I want to know which power to choose. And this is where somehow I was doing this by hand for ages and ages and ages, and Martin wanted to program it into the computer. And somehow there was this little thing that I was doing automatically, which we realized as we were discussing it, and this is what we call the 1, 2, 3 rule. Yeah, actually, I should say, what am I trying to do? I'm trying to build a fundamental polyhedron. So a fundamental polyhedron will be a 4-dimensional ball, topologically. Its boundary is going to be a 3-dimensional sphere. And so what I'm wanting to do is I'm wanting to have some sort of 3-dimensional pieces. This is one of my 3-dimensional pieces. And I want to put in the center of my domain, because it's actually not going to be a fundamental domain for the group, but rather for a coset decomposition. That's a sort of technical thing which you push under the carpet. But in the middle of the polyhedron, I want the fixed point of 1, 2, 3. So what I want is that if I just draw that as a cartoon, I could think of this. If this was these were the different powers of A, and here's the fixed point of 1, 2, 3. Then how do I? And I've chosen this one. I now need to choose this bottom one in one of several different ways. Well, it turns out that there's this thing we call the 1, 2, 3 rule, which is that whenever I have one of these triangles, that we would have to have that ABC or CAB is 1, 2, 3 in the group. So let's look at this example I had here. Well, here I have 1, 2, 3. That's fine. What about this one? Well, remember, I've still got a 1 at the bottom there. Well, I have 1, 3, 3 bars, 2, 3. Those cancel. That's 1, 2, 3. Now I'm going to be coming to the bottom side here. Well, it's going to be the other case, which is going to be the CAB. And if I've chosen this correctly, so in this case, I would have down here, I would have 1, 3, 1 bar, and 1, 2, 1 bar. Because that would be the image of this under reflection 1. And you can see that we still get this rule because we have that 1, 2, 1 bar, 1, 3, 1 bar, 1 is 1, 2, 3, and now that's CAB. See, whatever I said it was supposed to be. And this actually means that the apex of the top and the bottom pyramids, they're mapped to each other by the map 1, 2, 3, or its inverse. So it's just a little trick. But I think I'm losing people at this stage. But all I'm saying is there's a good way to, once I have one of these pyramids, to choose the correct one down here. You would see that 1, 2, 3 is just going to rotate this picture.
What kind of an isometry is 1, 2, 3?
Sorry?
It is 1, 2,
3
3.
should be elliptic of finite order.
Yeah, it has a unique fixed point.
It will have a unique fixed point. So I think what I'm going to do before carrying on is to just to try to convince you of what's going on by working through a little example. And this is one of the, this is probably the simplest. So I'm going to start out with a square pyramid with 1, 2, 3, 2, 3, 2 bar. So this is. Now, well, I'm going to have its. So I still have 1s all the way around here, then its image under 1, so that's going to be 1, 2, 1 bar, 1, 3, 1 bar. Sorry, 1, I've got this the wrong way around. 1, 3, 1 bar. Too close to the board. 1, 2, 3, 2 bar, 1 bar, and 1, 3 bar. And now I need to start to do the same trick. But what I need to do is, I need some other sides that are going to pair up to to this side parts of the pyramid, side triangles. I've got the bases sorted. Now I need to do the other way around. Yeah.
So John, these numbered edges, they in one sense they represent complex lines.
That's
Fixed
right.
points of these elements, but are they also literally? I guess they're geodesic segments.
They're going to be geodesic
fixed points
segments.
of
Yes, that's
particular
right, exactly.
finite
That's
element.
right. So the moment I'm just doing things combinatorially, I'm going to realise it geometrically in a moment. Well, my plan was to realise it in a moment. I'm sort of way over time. I can't remember even when I started.
Or you still have 5 minutes.
Sorry?
You still have 5 minutes.
5 minutes, okay, well, I'll see what I can do in 5 minutes. And then we start with another of these triangles, but we choose one of the other sides to be the base. And again, I use the 1, 2, 3 rule to decide which one is the base. So let's look at the back triangle for this. So I still have 1, 2, 3, 2 bar, and 3 bar, 2, 3. And now I'm going to choose 2, 3, 2 bar to be the base of that triangle. And it turns out that in the case that I'm interested in, that's just going to, I'm going to have a 3 braid, but this is now the top of it, of that my previous construction. And so this one here is going to be 1, 2, 1, 3 bar, 2, 3, 1 bar, because it's going to be those are my things that are braided. And so of course there's going to be another triangular pyramid in front and so forth. Okay, so that's this. We just play these little games. And then we get the computer to play little games as well, because there's too many little games to play. Good. So what we now do is we just keep repeating this process. We have more triangles, and at each time we know exactly which triangle, which one to choose as the base, using the 1, 2, 3 rule. And then we build its pyramid according to some braiding. We assume that all the vertices at the bottom braid to finite order, and I carry on going. And eventually, we assume, and we can check this, that this whole process fills up, continues to give me a 3-sphere. And actually checking that a manifold is a 3-sphere is quite easy. Now we have the Poincare conjecture, because all I need to do is sort of So I mean, in our previous paper, we actually showed that in this particular family, the union of all the square pyramids gave a solid torus, the union of all the triangular pyramids gave a solid torus, and that they had a common boundary and they fitted together like the hot which, you could do this in principle for the other cases. Okay, so how do we realize this geometrically? Now, when Rich was doing row chi, he went up to projective space and filled things in with linearly, and then project down it caused lots of problems because he needed to re-subdivide, and somehow that was using the natural geometry of projective space. We want to use the natural geometry in complex hyperbolic space, and so we're going to fill all of these things in with pieces of bisector. So I need to tell you briefly what about bisectors. Okay, if I have this is my complex hyperbolic 2 space, and let's suppose that I have a pair of points here. They're going to span a unique complex line. I can draw that. And the restriction of my Bergman metric to that complex line is just the Poincaré metric. So I know what the points equidistant from those 2 points are. That would just be a geodesic. We call this the spine of the bisector. And then there are 2 ways that this bisector is foliated by totally geodesic hypersurfaces. One way is that for every point on this spine, I look at the complex line that is the pre-image under orthogonal projection onto this brown complex line. And the other way, I'm going to colour, having scattered them around the room. Thank you. You've rested me. Yeah, very good. Is that I could take all totally real Lagrangian subspaces containing this spine. So a better way to draw it would be to think of it as being this ball. This is a ball like this, and I have all of the totally real Lagrangian planes like that. And if I come back to where the yellow was, which I lost it, line yellow to be brown, and then I have complex lines all the way through. I can actually extend this out into complex projective space, and a point over here is going to exactly be orthogonal to one of these lines, and so that's the duality between those points and the lines. So when I have one of these pyramids, I'm going to choose a bisector so that this point lies on the spine, on the green line, and that this base, which is in a complex line, should be one of these slices, one of these horizontal lines here, which corresponds to another point on this circle. So this is going to be one of these slices. And if I do that, it turns out a little geometrical argument shows that the one skeleton of this, all these geodesics are all contained in this bisector. Now, I slightly lied to you because that's assuming that all of these points lie on the inside of complex hyperbolic space. But just like with Coxeter groups, you can have ultra-ideal vertices, in which case I would have to truncate this top. And similarly, what would happen is I would end up truncating, I could truncate somebody down here. And so there are various different possibilities for how these sides could be, but in all cases, the one skeleton, geodesic one skeleton between these points are all in the bisector. All points are fixed points of a particular elliptic element, so they're determined for me. And so I then take these fixed points and I join them up with geodesics. That automatically sits inside a bisector. Then what we then need is that actually this geometric realization actually is a polyhedron. So then we need to check whether everything is nicely embedded, and that things that were combinatorially distinct are really geometrically distinct. And this is where we quite heavily use Martin's computer program, so it's not experimental in the sense that it's exact computations over a number field that he's doing to prove all of this. So it's all of these computations could, in principle, be done by hand given a lot of people and a lot of scrap paper. But, so they are precise, rigorous computations to determine that this really is a polyhedron. And then we need to apply the Poincare polyhedron theorem to check that all of my angles, conditions, and everything all work, so that the group is in fact discrete, and that will then prove that it's a lattice. That's basically how our algorithm works and how our program works. It gives you a new construction for the Deligne and Mostow groups. It also works for these extra groups that we have found. And so using this, we've extended the number of commensurability classes of non-arithmetic lattices. So Deligne and Mostow, there are 9 commensurability classes in SNPU21 on their list. We've got a further 13, so we've extended it to 22, which only doesn't sound very, very big. Hopefully there's going to be infinitely many if we have better ideas. But I hope that these few examples could start as building blocks to find more than one example in the next dimension up. And that's really where the project should be going next. Okay, so thank you for your attention.
What's the degree of the number of fields you get?
Most of the time it's quadratic, sometimes it's degree free. And they're the sort of number fields that you might. I mean, I think there's one complicated one. I think it's degree 4. It might have degree 6, but most of the time they're
Okay.
You're talking about the K.
yeah. So most of the time they're things like Q would join I root 3, or Q would join 1 plus I root 7 over 2, or Q would join.
The whole number field, not the real time.
Yeah.
K is the reason. Yeah, I know. I thought you.
Yeah.
That's
So
I-
yeah. So the okay. So yeah, or perhaps a degree 2 extension of that if I've just mentioned the real part. But yeah, so Q would join I root 3 would be one of them, for example. That happens quite a lot. Yeah.
Did you try quadrilaterals? I mean,
That's the obvious question. Yeah, we haven't. There's lots of things that we could try. We sort of there's a little bit of way of trying lots of things. We haven't really got a good strategy for doing.
Quadrilaterals would depend on continuous parameters now. Because your discussion very soon.
Yeah, well, they're continuous parameters, but I very soon went down to like triangles depend on continuous parameters. But as soon as I go to triangle
all
groups,
these
I
trace
think I think
relations
of
would
integers.
probably make it.
Like only discrete matrices. This would work the same for quadrilaterals.
Maybe.
Presumably.
Yeah.
So you cover the example up to commensurability, exactly the same, or
Yeah.
up to commensurability.
We recover all of Mostow's examples exactly on the nose, and then there's a bit of commensurability that happens.
So this Deligne and Mostow thing were constructed by looking at some kind of generalized hypergeometric equations, right? Somehow, can you solve the inverse problem here and look for the equation in your case,
So
which would give an additional?
So I can give you part of an answer to that question. The classical construction for triangle groups is that that gives you monodromy for classical hypergeometric functions. So this is like Schwartz in the 1870s. Yeah. Now, you can generalize that in 2 ways. What Deligne and Mostow did, following Picard, was to generalize it to hypergeometric functions in several variables. And more or less that's a closed story, because on this Deligne and Mostow list, they've shown all the possible lattices that could arise in this listed. So you actually want to do something different, and you can, if you go to what's called a generalized hypergeometric function, one variable, so there's work of Boykers and Heckman, for example, They show that if you have a group generated by two elements of finite order, matrix group generated by two elements of finite order, whose product is a complex reflection, then that is the monodromy group of one of these generalized hypergeometric functions. And all of our non-arithmetic lattices actually arise in that way. So we can describe them as monodromy of certain differential equations. I'm trying at the moment to get my head around exactly what those differential equations look like in this particular example.
So after the fact, are these fundamental domains Dirichlet cells with respect to the central point?
They somehow have little pieces of them that start to look like Dirichlet cells, and then suddenly they move to. No, I mean Martin's original did some experiments with Dirichlet domains, and so the one that we had over here, there's not very many faces. This particular example that I did up there, there were 28. Right? And when he was doing it for some of these same groups of Dirichlet polyhedra, he was getting things with hundreds of thousands of signs.
I see, that's why you do this, to kind
So
of
that's that.
micromanage.
Yeah, I mean, we could in principle do it for Dirichlet polyhedra, but there would be more calculations than and we couldn't make his things into an exact computation in that case, because at some point you need to choose a degree of resolution, and you may well have some very, very tiny faces that are below that degree of resolution, however high your precision. So there was no way we could actually work that out. So we chose a different construction that somehow sort of feels a little more like it's inspired by your paper. Just got to be good, right?